we're going to talk about regions of a planar representation of a connected graph in this video. First, let me point out that if you have a connected planar graph and a planar representation of it, that is often called a map. That's very common language for that. And we are going to look at what are called the regions, which will be the two-dimensional sections of the plane that are bounded by the edges of the graph, or whose boundary is consists of the edges of the graph. So in this case here, there are, let's see, I'll tick them off here, 2, 3, 4, 5 bounded regions, but then there's this other one out here, an 8th region, which is unbounded. So those are the regions. Exactly one region will be unbounded, and the region can be given a degree which consists of the length of a closed walk of minimal length that traverses all bounding edges of the region. All right, so that's a little wordy there. You'll want to look at that again. What we're going to do is get a closed walk that traverses all the edges, and do so in a minimal way to capture the degree or determine the degree of a region. Some of these are going to be pretty simple, and so let me get rid of these check marks here, and we'll go back, and in each region we'll list its degree. So for example, this one right here is fairly obvious. This one right in here that I put the dot in, if you take a closed walk that starts here, it will take 1, 2, 3, 4 edges to get a closed walk, and obviously that's the smallest, so this has a degree of 4. Likewise, this one right here, to the far right now, has a degree of 3, and this one right next to it has a degree of 1, 2, 3, 4. That's also a 4. So take a moment, maybe pause this, and see if you can find the degrees of the other regions in this case. Alright, I'm going to go ahead and proceed with it. And the degree of this region right here, well, let's see, we've got to include all edges in the boundary, and this one jutting out here is an edge of the boundary. If you think about this being an area we're going to walk, and this is a wall here, you can't walk through the wall. It actually is something that is restricting you, that is part of the boundary. So a closed walk that goes over each of the edges in the boundary, I don't know, let's start it anywhere you want. Let's start it here, for example, and let's go in this direction here. So we're just walking all the edges in the boundary. Come over here. We're going to have to walk that one that juts in there. So this is 1, 2, 3, 4, 5 to go in. I have to come out. That's 6 to come out. 7, 8. That actually has a degree of 8. And notice that that pendant vertex counted twice here. In the same way, in the unbounded region, we're going to have this pendant vertex. It's poking into the unbounded region. That is the region it serves as part of the boundary for. And so let's take our closed walk, and this line, let's just start it there. So closed walk starts here. I'll use the green to get a different look of it. Then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this has a boundary or a degree, sorry, of 10. So there's only one region left. I think when I first counted these, I must have overcounted. There's one here, and let's see what that one would be. So again, you might try it. I'm going to go ahead with it. So in this case here, let me go ahead and use the red here to get that. So 1, 2, 3, 4, 5. Now you might think we'd be done, but all this stuff inside is also a boundary separating this room, so to speak, from anything else. So I'm at 5, 6, 7, 8, 9, 10. I started right here So there we have an 11. Okay, 11 right there. So that has a degree of 11. So it has how many regions? 1, 2, 3, 4, 5, 6 regions, and the degrees of the regions are listed within them. And notice, although I haven't colored every edge here, I didn't do that with every one of these when I did this. But let's just pick this one edge right here that is uncolored. It's just, well, now it is. It's red. That edge right there in red. Notice that when I calculated this degree of this region here, 4, it counted towards that one, but it also counted towards the 3 here. So it counted twice. This green one counted each time we went over it. It counted twice. Let's see. Yeah, this one here that is a boundary right here is a boundary of the one that we just counted with 11, counted towards the 11, but it also counted towards the 10 for the unbounded region. Each edge counted twice, so if we were to add the degrees of the regions, 4 plus 4 plus 3 plus 8 plus 11, 10, well, 10 and 11, right? Those are all of them. 1, 2, 3, 4, 5, 6. What do we get out of that? That's just, I see a 8 and an 8, 16. And then we have a 26. And 14 from those two gives us 40. Right? So what should that equal with regard to the graph? Well, this edge counted twice. It counted 2. This edge counted 2. This edge counted 2, and so forth. So if we count the number of edges, let's see if we can do that without getting too confused here. 1, 2, there's 1, 2, 3. I'll just go outside. 4, 5, 5, 6. There's a little one here. 7, 8, 9. Those are the ones outside. So on the inside, I'll have that's going to be a little confusing with these other numbers. I'll get rid of some of them. So on the inside, I'll have a 10, 11, 12, 13, 14, 15, 16. So I think I've got all of those counted. And let's go over count here, any that I've missed. 17, 18, 19, and 20. So 20 edges. Well, indeed, 40, which counts each of the edges twice, is 2 times the number of edges, which is 20. And that is, in fact, a theorem that is based on exactly what we did there. If you have a planar graph and R is a set of regions in the planar representation, then the sum of the degrees of the regions, taking all possible regions little r out of a set of regions R, is 2 times the number of edges there. Right. So there's nothing here that actually depended on the connectedness of the graph. This is valid whether or not it's connected. Okay. That's a very nice representation. It's very similar to one. So recall in a graph. By the way, there's nothing here that prohibits multiple edges or loops. In a graph, the sum of the degrees of the vertices is also twice the number of edges. Right? So those two things are going to agree when you have a planar representation of a planar graph. So the one that we just derived is a little more limited in its scope. It doesn't apply to all graphs, but it does apply to those that are planar, and we have a specific planar representation. Right, so what we're going to do with this next is to derive a formula called Euler's formula, and I think for that I'll go ahead and stop this particular clip and we'll come back to Euler's formula.